Alright, we got some things chopped up, but we're going to be focusing on A, C, E, and J of 2.2.2. And if I can't do one of them, we're going to stop. So we're going to go till we can't anymore, which is following our subspaces of R3. Justify your answers. Over here we have the definition of what a subspace is. A subspace of vector Z is a subset W. So we have a big old space V. W is just a subset of V. If it is a vector space in its own right, which means that it's closed under vector addition, scalar multiplication, and includes the zero element. Okay? Because if V is a vector space and W forms its own vector space, that means that if you have two vectors that are in W, let's say, what's the name of the vectors, x1 and x2. If you add x1 and x2 together, if that is still, whatever answer you get over here, is still a member of W, then you're good. Also, you have to figure out, does W include the zero vector? If it doesn't, then it can't be a subspace because you need the zero vector to do linear algebra. So a vector space is just something you do linear algebra with, okay? So you can do linear algebra with it and you don't lose that quality of the thing. So meaning you don't, when you add something together, it stays in the vector space. When you multiply under linear combinations, if you have C1, C2, then you still end up with getting an element that's in W. So if that's still in W, then it is a vector space. So that's essentially what we're going to be doing today, is we're going to check, does this vector space include the zero element? Is it closed under addition? If we add two vectors in the subspace together, do we get a vector that's in the subspace? And then in that space, subspace. And then we're going to see if we have a constant multiplied through, are we still going to, if we multiply it by a constant, do we still get something that's in that subspace? Okay. Might seem kind of arbitrary, but it will make more sense as we go along. Okay. The set of all vectors satisfying x, y, and z, and I included my own here just to make it different from the book. This is a plus 2 equals 0. Is it a subspace? Well, we can think of plugging some elements in here and getting it to equal 0. So if x equals 1, y equals 1, and z equals 0, then, yeah, then this is closed. Because these two added together, well, if these equal -1, my bad, -1. So this contains 0. 0 vector. CTOR. Okay. Now, first condition, check. Second condition, can we add two of them together and still have an element in the subspace? So let's take x1 plus y1 plus z1. And if we add that, let's write it vertically. X, y, z. 1, 1, 1 plus x2, y2, z2. Is this in the subspace? I would say, if we add them all together, is this vector still in the subspace? So, when we add x1 plus y1 plus z1, according to our equation, we get this to equal -2. x2 plus y2 plus z2 equals -2. So given that this is the case, when we add them together, so let's add this row and this row, and then we add both sides of this, we're going to get it that it equals -4. So this can't be closed under vector addition. So therefore, if it doesn't have closure under vector addition, we'll just write that, not closed under vector addition. All right, we'll just leave it at that. So A is not a subspace. Let's do B. I mean C. Set of vectors that have the form R minus S. Try it a little smaller. R minus S. That's not much smaller. R plus 3S. Negative S. Alright, where R and S are real numbers. Okay. So, real numbers include 0. Let's see. 0 condition. 0 minus 0. 0 plus 3 times 0. -0. That equals the 0 vector. First condition met. Alright, let's take two vectors. We'll see if we can add them together. So our first vector will be R1 minus S1, R2 plus 3, not R2, R1 plus 3S1, negative S1. And we add that to R2 minus S2, R2 plus 3S2, negative S2. Do we still end up with something that fits in here? All right. Let's see. R1 minus S1 plus R2 plus S2.